Welcome back to our channel. In last video we have seen performance curves of hydraulic turbines, and in this video we will see some sample numericals on reaction turbine. In previous video of numericals of Pelton wheel turbine, we got some comments or feedback that in one video it is very fast explanation. So for these four problems we are making two videos, part 1, part 2, so that it will be helpful for you for better understanding of problems. So before starting problems, let's see formulas for reaction turbines. So this is the velocity diagram. Inlet velocity triangle, absolute velocity is making angle alpha, then relative velocity making angle theta at inlet. This is also called as moving blade angle. Alpha is a guide blade angle. For V1 we are making two components. One is perpendicular, radial, and second one tangential. This is V1, VW1. At outlet for Francis turbine, Kaplan turbine, discharge is radial, so all V2 is equal to VF2. There is no any VW2 at outlet, but relative velocity is moving along blade profile. It is making angle phi at outlet, and difference between these two vectors is linear velocity at outlet, and this is the linear velocity at inlet. Okay, now for Francis turbine, discharge is area into velocity of flow. Okay, so area is pi d1b1 vf1 at inlet. Sorry, area is pi d1b1 are diameter and width at inlet, and d2b2 diameter and width at outlet. So at outlet it becomes pi d2b2 vf2. If there are number of blades are given, and if each blade is having thickness t, then out of pi d n into t, this portion will be covered by our blades, so this is not available for flow. So total area is pi d minus nt into b we have. Okay, then this is for velocity. If they are given speed ratio is u1, so it is given speed ratio is for u1, not for u2. So u1 is equal to phi s under 2gh. Then flow ratio also it is defined for inlet, so vf1 is equal to phi f under 2gh. Then power developed by turbine or rotor power is equal to rho q, that is mass flow rate, into vw1 e1, because vw2 is 0 at outlet. Then hydraulic efficiency, rotor power upon water power, it is equal to w1 e1 upon gh. We have derived this equation. Then mechanical efficiency is shaft power upon rotor power. Overall efficiency is shaft power upon water power. Next is water power. It is simply rho q gh. Then for Kaplan turbine, velocity diagram remains same as it is, but there are some correlations. It is vf1, velocity of flow at inlet and outlet, remains constant, so vf1 is equal to vf2 here. It is equal to phi f under 2gh, and linear velocity at inlet and linear velocity at outlet is same, and that is equal to phi s under 2gh. This is speed ratio, this is flow ratio. Again, this linear velocity is calculated for outer diameter or rotor diameter, outer diameter or wheel diameter, not for hub diameter. Discharge, as flow is axial, discharge is again qa to velocity of flow. Here area is cross sectional area, it is outer diameter minus hub diameter, pi by 4 do square minus dv square to velocity of flow. These are the some formulas. Again, these are repeated formulas. Unit quantities, nu is equal to n upon root h. Unit discharge is q upon root h. Unit power power upon h raised to 3 by 2. Here power is in kilowatt. Again specific speed is equal to n root p h raised to 5 by 4. Here again power is in kilowatt. Then we have derived model relationships in last chapter. These relations remain same as it is. This head coefficient is equal to h upon n square d square. And flow coefficient, discharge coefficient is q upon n d cube constant. And power coefficient p upon n cube d raised to 5 is equal to constant. Then again this is an important one, draft tube. And draft tube efficiency is equal to v1 square upon 2g minus v2 square upon 2g minus hf upon v1 square upon 2g. v1 v2 are the velocity of flow at draft tube inlet and draft tube outlet. Okay, hf is the head loss in this draft tube. Then again, if they are given pressure gauge reading or vacuum gauge reading, then this formula changes to vacuum gauge reading upon rho g, or vacuum head minus height above tail race. So this is the height above tail race, not draft tube height. Okay, upon v1 square upon 2g. So these are the some formulas which are useful for solving numericals in this chapter. So let's start one by one. Okay, so this is the first problem we are going to discuss. Problem is a Francis turbine with overall efficiency 75% is required to develop 25 kilowatt power. It is working under head of 7.62 meter. The linear velocity is 0.26 under root 2gh and radial velocity is 0.96 under root 2gh at inlet. Okay, if wheel runs at 150 rpm, if wheel runs at 150 rpm, wheel runs at 150 rpm and hydraulic efficiency is 78%, assuming a radial discharge at outlet, determine guide belt angle, wheel vane angle at inlet, width of runner at inlet. So first see what is the given. First, overall efficiency is given here 75%. Overall efficiency is given 75%. Then develops power. So this is the shaft power given 25 kilowatt. Working under head means head over turbine is given. Then linear velocity at inlet. So u1 is equal to relation given 0.26 under root 2gh. Same for velocity of flow at inlet. Radial velocity means velocity of flow at inlet is given 0.96 under root 2gh and speed is given 150 rpm. Okay, and their hydraulic efficiency is also given 78%. And they have asked calculate what is alpha, that is guide belt angle, wheel vane angle at inlet, that means theta, and width of runner at inlet, that means bi. So first draw this velocity diagram, v1, vr1, vf1, vr2, v2. Always draw velocity triangle for hydraulic problems. Now here first they have asked alpha. So alpha is in inlet triangle, so this is our alpha. So for alpha we can write this alpha is equal to, or tan alpha is equal to this vertical height upon this horizontal height. So tan alpha or alpha is equal to tan inverse of opposite side vf1 upon horizontal side vw1 or adjacent side vw1. Then for vf1 relation is given, so we can calculate vf1 directly, h is given directly, so we get this value. Okay, then for vw1, here vw1 is not given. Remember always in case of Francis turbine problems, hydraulic efficiency is always given to calculate vw1. Okay, so they have given hydraulic efficiency. In hydraulic efficiency we have formula vw1 v1 upon gh. Here we have to find out what is VW1. For that purpose they have given hydraulic efficiency. H is given, G is constant. For U1 they have given relation, so U1 can be easily find out, and this value comes to be 3.179 meter per second. And putting this value in above equation, we get VW1 as 18.34 meter per second. Put this value in our first equation, and here VF1 is known, here VW1 is also known to us now. Then alpha is comes to be 32.6 degrees Celsius, degrees. Then next ask quantity is theta. Again theta is in inlet triangle, so again for theta we can write this tan of theta is equal to this height upon this height or this length. This length is equal to VW1 minus E1. This only part is VW1 minus U1, so our theta will be tan inverse of F1 upon VW1 minus U1. Here we have calculated VF1, then we have calculated U1, and also we have no VW1, so theta comes to be 37.42 degrees Celsius. Now they have asked B, that is dimensions of rotor. For dimensions of rotor, remember always use discharge relations, or discharge relations are given for calculating dimensions of rotor. So Q is equal to, we know values of VF1 here, so using at inlet, Q is equal to pi d1 b1 VF1, out of which VF1 is known, then pi is constant. Q, if we want to calculate b1, then we have to first find out what is value of d1 and what is value of Q. For d1 use inlet velocity relation, this is equal to pi d1 n upon 60. Here u1 is calculated, d1 n is known, so by using this relation you can calculate d1, and it is coming 0.4047 meter. Now next is discharge calculation. Remember that as hydraulic efficiency is given for VW1 calculation, overall efficiency in problem is given for mostly calculation of discharge. So for overall efficiency, formula is shaft power upon water power. It is shaft power upon rho QGH. Here shaft power is given 25 kW, rho is known for water, G is known for constant, and H is known. So all quantities are known, then Q can be easily calculated. It is coming 0.44 meter cube per second. Then put all these values in our discharge equation. Now Q is known, D1 is known, V1 known. Calculating, we get B1 as 0.029 meter. Okay, remember all calculation is not possible here. I will explain steps, and I suggest you to do calculation at your own. If there are some changes or corrections, please let us know. Okay. Next problem. Okay. Next problem is a hub diameter of Kaplan turbine working head of 2 meter is 0.35 times outer diameter. Runner is running at 100 rpm if vane angle at extreme edge of runner outlet is 15 degree, and flow ratio is 0.6. Find diameter of runner, discharge through runner, and diameter of boss. So given first is head 2 meter, then relation is diameter of boss is 0.35 times diameter of outer diameter, that means dB is equal to 0.35 times of do. Okay, this is the relation given. Speed is given 100 rpm. Then vane angle at extreme edge of runner outlet, so this is phi. Vane angle at outlet is denoted by phi, it is 15 degree. And velocity of flow ratio is given 0.6, that means Vf1 is equal to 0.6 under root 2gh. This is the relation. They have asked base diameter, discharge, and outer diameter, boss diameter, runner diameter, and discharge. Then again draw velocity triangle. For Kaplan turbine by default outlet is radial, so it is velocity angle comes to be this. Now again base diameter, so this is the base diameter. We have relation u is equal to pi do n by 60. Then we know that to calculate outer diameter, first they have given n, so we have to first calculate u. Okay, and for u they don't given diameter, or they don't given any speed ratio. So for u we know that u is equal to u1 plus u2. Okay, u is equal to u1 plus u2 for coupled turbine. So at outlet they have given phi, so we are considering outlet triangle. At outlet triangle, if you take tan of phi, then it will be vf2 upon u2. So tan phi is equal to vf2 upon u2. Here we can calculate vf1 as for coupled turbine, vf1 is equal to vf2, so we can calculate or get vf2 directly. Then phi is given, so we can get directly tan phi. Then knowing values of u2 and tan phi, values of vf2 and tan phi, we get values of u2 easily, and this is coming 34.35 meter per second. Now to find out do or outer diameter, put this u2 value in this equation. We will get outer diameter as 6.561 meter. Okay, so this is the outer diameter. Now relation between outer diameter and base diameter is given. By using this relation, our outer diameter coming 0.35 times of outer diameter is equal to 2.296 meter. Okay, then discharge, as turbine is axial flow turbine, axial flow or coupled turbine, u will be equal to pi by 4 do square minus dB square into Vf. Velocity of flow is known, dB is known, do is known. Putting this value, we will get answer q is equal to 272.98 meter cube per second. So these are the first numericals. Now let's take remaining numericals we will see in our next video or second part. Thank you for watching. If you have any suggestions or corrections in calculations, please contact us and provided number. Thank you.